Welcome to section 6.3, orthogonal projections. In this section, we are going to learn how to identify orthogonal projections and how to find them. And this is going to help us solve the least square problems that we will see in the final section of this class, which is section 6.5. So the end is near. A lot of the material that you'll see in this video are very familiar items, so we are going to basically be reviewing. So if I want to project one vector onto another, then we have this y hat, which we saw in the previous section. So here, this is projecting vector y onto u, as illustrated here. So I have provided a little diagram for you this time. So if we are given a vector y in Rn and a subspace W, then there is a unique vector y hat that is closest to y and y minus y hat. And that is orthogonal here. So two things, it's a unique vector and closest to y. So this brings us to theorem 8, which is the orthogonal decomposition theorem. And it should look pretty familiar. These are things that we've seen before. I want to remind you of some notation. This here is from section 6.1, and it denotes the set of all vectors orthogonal to a subspace W. Okay, and so y hat and z are things that we've seen before. Now you might be thinking, why in the world are we doing this again? We just saw the same thing. Well, in the previous section, we were dealing with when W was a one-dimensional subspace. So the formula for y hat then matched the formula given in section 6.2. So now we have different dimensions. So let's jump into this. So recall that the vector y hat is called the orthogonal projection of y onto W and is sometimes denoted in this way. So what we are asked to do, we're given the same type of information we were given in the previous section, and we want to write y as a sum of vector W and a vector orthogonal to W. So what I want to do here is I want to find y hat, and remember this is found by the following formula: y dot u1 divided by u1 dot u1 times vector u1 plus y dot u2 over u2 dot u2 times vector u2. So this here is found in the following way. When I find this, I get 9/30 times vector u1, which is this guy here, so 2, 5, -1, plus when I find this, I get 3/6 times vector u2, which is this guy here. And so then I can find the sum of these, which gives me -2/5, 2 1/5. Okay, so that is y hat. And then if I want to find z, z is equal to y minus y hat. So we know vector y is 1, 2, 3, and we just found y hat here. So if I subtract those, I get 7/5, 0, and 14/5. So ultimately, we want to write y as a sum of a vector in W and a vector orthogonal to W. So what I'll do is I will say that y is equal to the sum of this and this. And you can verify that the sum of these two things equals that. So just to write it up, y is equal to this vector, which is the sum of these two vectors. And that concludes this example. Now, I know that some of you like illustrations, so this here is an illustration of what we just found. So when the dimension of W is greater than 1, each term is an orthogonal projection of y onto a one-dimensional subspace that is spanned by one of the vectors in the basis. So this little diagram here can be found on page 351, and there's a nice little write-up about it if you have the desire to see this visually. So this here is Theorem 5 from section 6.2. So we have seen this notation before. So here, this represents the orthogonal projection of vector y onto W. So now in this theorem, what we're interested in finding is the vector that is the closest point in W. So y hat is the closest point in W to y. So sometimes you're asked to find the closest point, then you find y hat. So y hat is the best approximation to y by elements in W. So here is an example. So if I use the vectors from the previous example and I want to find the closest point in W to y, it is simply y hat, which we found previously. So this here is the closest point to y. Okay. The last example that I'm going to show you in this section is how to find the distance from y. So that is going to utilize the information that I just showed you for the best approximation. So let's go ahead and use the best approximation theorem. Okay, so if I'm going to use the best approximation theorem, remember the distance from y to W is y minus y hat. So remember this represents the length, and that comes from section 6.1. So if you have forgotten this notation, go back and review length from section 6.1. Okay, so this is what we need to find. So the first thing we want to do is we want to find y hat. So y hat, we've done this a lot. So it is 15/30 times vector u1 plus negative 21/6 times vector u2. So if I reduce this, I have 1/2 times this vector, 5, negative 2, 1, minus 7/2 times this vector, 1, 2, negative 1. And if I apply those scalars and combine those vectors, I end up with this vector for y hat. Great. Okay, so now I'm going to take y minus y hat, which is -1, -510, minus -1, -8, 4. This gives me the vector 0, 3, 6. So now what I want to do is find the length of that, because this is going to give me the shortest distance, the distance from y. Okay, so when I do this, I'm going to have y minus y hat. Oops. And there are a couple different formulas to find this length in section 6.1. I'm going to use this formula, and I didn't use this very, I don't know if I used it at all in my previous videos, but it's the same thing. So this would give me 3 squared plus 6 squared, which is 45, and then the distance from vector y to w is the square root of that. So the square root of 45, which can be reduced to 3 root 5. And there you have it. Not so bad for an under 12-minute video. Woo!